In this video, I will give you a complete overview of Kubernetes services. First, I'll explain shortly what service component is in Kubernetes and when we need it. And then we'll go through the different service types: ClusterIP Service, Headless Service, NodePort, and LoadBalancer Services. I will explain the differences between them and when to use which one. So by the end of the video, you will have a great understanding of Kubernetes services and will be able to use them in practice. So let's get started. So what is a service in Kubernetes and why do we need it? In a Kubernetes cluster, each pod gets its own internal IP address. But the pods in Kubernetes are ephemeral, meaning that they come and go very frequently. And when the pod restarts, or when old one dies and the new one gets started in its place, it gets a new IP address. So it doesn't make sense to use pod IP addresses directly, because then you would have to adjust that every time the pod gets recreated. With a service, however, you have a solution of a stable or static IP address that stays even when the pod dies. So basically, in front of each pod, we set a service, which represents a persistent, stable IP address, access that pod. A service also provides load balancing, because when you have pod replicas, for example, 3 replicas of your microservice application or 3 replicas of MySQL application, the service will basically get each request targeted to that MySQL or your microservice application and then forward it to one of those pods. So clients can call a single stable IP address instead of calling each pod individually. So services are a good abstraction for loose coupling for communication within the cluster, so within the cluster components or pods inside the cluster, but also from external services, like if you have browser requests coming to the cluster, or if you're talking to an external database, for example. There are several types of services in Kubernetes. The first and the most common one that you probably will use most of the time is the ClusterIP type. This is a default type of a service, meaning when you create a service and not specify a type, it will automatically take ClusterIP as a type. So let's see how ClusterIP works and where it's used in Kubernetes setup. Imagine we have a microservice application deployed in the cluster. So we have a pod with microservice container running inside that pod. And beside that microservice container, we have a sidecar container that collects the logs of the microservice and then sends that to some destination database. So these 2 containers are running in the pod. And let's say your microservice container is running at pod 3000 and your logging container, let's say, is running on port 9000. This means that those 2 ports will be now open and accessible inside the pod. And pod will also get an IP address from a range that is assigned to a node. So the way it works is that if you have, for example, 3 worker nodes in your Kubernetes cluster, each worker node will get a range of IP addresses, which are internal in the cluster. So for example, the pod 1 will get IP addresses from a range of 10.2.1 onwards. The second worker node will get this IP range, and the third worker node will get this one. So let's say this pod starts on node 2, so it gets an IP address that looks like this. If you want to see the IP addresses of your pods in the cluster, you can actually check them using kubectl get pod output wide command, where you will get some extra information about the pods, including its IP address. And here you will see the IP address that it got assigned. And as I mentioned, these are from the IP address range that each worker node in the cluster will get. So this is from the first worker node, and these are from the second worker node. So now we can access those containers inside the pod at this IP address at these ports. If we set the replica count to 2, we're going to have another pod which is identical to the first one, which will open the same ports and it will get a different IP address. Let's say if it starts on worker node 1, it will get an IP address that looks something like this. Now, let's say this microservice is accessible through a browser. So we have ingress configured, and the requests coming in from the browser to the microservice will be handled by ingress. How does this incoming request get forwarded from ingress all the way to the pod? And that happens through a service, a ClusterIP or so-called internal service. A service in Kubernetes is a component just like a pod, but it's not a process. It's just an abstraction layer that basically represents an IP address. So service will get an IP address that it is accessible at. And service will also be accessible at a certain port. Let's say we define that port to be 3200. So ingress will talk to the service or hand over the request to the service at this IP address at this port. So this is how service is accessible within the cluster. So the way it works is that we define ingress rules that forward the request based on the request address to certain services. And we define the service by its name. And the DNS resolution then maps that service name to an IP address that this service actually got assigned. So this is how ingress knows how to talk to the service. If you don't know how ingress works, I have a separate video where I explain ingress, all its concepts, and how to use that. So you can check out that video to learn more on ingress itself. So once the request gets handed over to the service at this address, then service will know to forward that request to one of those pods that are registered as the service endpoints. Now here are two questions. How does service know which pods it is managing or which pods to forward the request to? And the second one is, how does service know which port to forward that request to on that specific pod? The first one is defined by selectors. A service identifies its member pods or its endpoint pods using a selector attribute. So in the service specification, in the YAML file from which we create the service, we specify the selector attribute that has a key value pairs defined as a list. Now these key value pairs are basically labels that pods should have to match that selector. So in the pod configuration file, we assign the pod certain labels in the metadata section. And these labels can be arbitrary names. So we can say my app, for example, and give it some other labels. This is basically something that we define ourselves. We can give it any name that we want. These are just key value pairs that identify a set of pods. And in the service YAML file, then we define a selector to match any pod that has all of these labels. This means if we have a deployment component that creates 3 replicas of pods with label called app my app and type microservice, for example, and in the service selector attribute we define those 2 labels, then service will match all of those 3 pod replicas, and it will register all 3 pods as its endpoints. And as I said, it should match all the selectors, not just one. So this is how service will know which pods belong to it, meaning where to forward that request to. The second question was, if a pod has multiple ports open where 2 different applications are listening inside the pod, how does service know which port to forward the request to? And this is defined in the targetPort attribute. So this targetPort attribute, so let's say targetPort in our example is 3000. What this means is that when we create the service, it will find all the pods that match this selector. So these pods will become endpoints of the service. And when the service gets a request, it will pick one of those pod replicas randomly because it's a load balancer, and it will send the request it received to that specific pod on a port defined by targetPort attribute. In this case, 3000. Also note that when you create a service, Kubernetes creates an endpoints object that has the same name as the service itself, and Kubernetes will use this endpoints object to keep track of which pods are members of the service. Or as I said, which pods are the endpoints of the service. And since this is dynamic, because whenever you create a new pod replica or a pod dies, the endpoints get updated, so this object will basically track that. And note here that the service port itself is arbitrary, so you can define it yourself, whereas the target port is not arbitrary. It has to match the port where container, the application container inside the pod, is listening at. Now let's say our microservice application got its requests from the browser through ingress and internal ClusterIP service, and now it needs to communicate with the database to handle that request, for example. And in our example, let's assume that the microservice application uses MongoDB database. So we have two replicas of MongoDB in the cluster, which also have their own service endpoint. So MongoDB service is also of ClusterIP, and it has its own IP address. So now the microservice application inside the pod can talk to the MongoDB database also using the service endpoint. So the request will come from one of the pods that gets the request from the service to the MongoDB service at this IP address and the port that service has open. And the service will again select one of those pod replicas and forward that request to the selected pod at the port, the target port defined here. And this is the port where MongoDB application inside the pod is listening at. Now let's assume that inside that MongoDB pod, there is another container running that selects the monitoring metrics for Prometheus, for example. And that will be a MongoDB exporter. And that container, let's say, is running at port 9216. And this is where the application is accessible at. And in the cluster, we have a Prometheus application that scrapes the metrics endpoint from this MongoDB exporter container from this endpoint. Now that means that service has to handle two different endpoint requests, which also means that service has two of its own ports open for handling these two different requests. One from the clients that want to talk to the MongoDB database, and one from the clients like Prometheus that want to talk to the MongoDB exporter application. And this is an example of a multi-port service. And note here that when you have multiple ports defined in a service, you have to name those ports. If it's just one port, then you can leave it, so to say, anonymous. You don't have to use the name attribute, it's optional. But if you have multiple ports defined, then you have to name each one of those. So these were examples of ClusterIP service type. Now let's see another service type, which is called Headless Service. So let's see what Headless Service type is. As we saw, each request to the service is forwarded to one of the pod replicas that are registered as service endpoints. But imagine if a client wants to communicate with one of the pods directly and selectively. Or what if the endpoint pods need to communicate with each other directly without going through the service? Obviously, in this case, it wouldn't make sense to talk to the service endpoint, which will randomly select one of the pods, because we want the communication with specific pods. Now, what would be such a use case? A use case where this is necessary is when we're deploying stateful applications in Kubernetes. Stateful applications like databases, MySQL, MongoDB, Elasticsearch, and so on. In such applications, the pod replicas aren't identical, but rather each one has its individual state and characteristic. For example, if we're deploying a MySQL application, you would have a master instance of MySQL and worker instances of MySQL application. And master is the only pod allowed to write to the database, and the worker pods must connect to the master to synchronize their data after master pod has made changes to the database. So they get the up-to-date data as well. And when new worker pod starts, it must connect directly to the most recent worker node to clone the data from and also get up to date with the data state. So that's the most common use case where you need direct communication with individual pods. So as you see, deploying and managing stateful applications like databases in Kubernetes is pretty complex, and that's why we need special type of components for them in Kubernetes. However, there are alternatives for working with SQL databases in Kubernetes much easier, like CockroachDB, our sponsor for this video. CockroachDB is a cloud-native distributed SQL database suited perfectly to Kubernetes. CockroachDB handles the messy details of keeping your data replicated in a consistent way, even with all sorts of failures. When you run CockroachDB on Kubernetes, you'll have a great combination of CockroachDB's built-in replication and survivability model and Kubernetes process management. And this will help you create highly available stateful applications in Kubernetes. So going back to our example of how client can know pods IP addresses, for such case, for a client to connect to all pods individually, it needs to figure out the IP address of each individual pod. One option to achieve this would be to make an API call to Kubernetes API server, and it will return the list of pods and their IP addresses. But this will make your application too tied to the Kubernetes specific API. And also this will be inefficient because you will have to get the whole list of pods and their IP addresses every time you want to connect to one of the pods. But as an alternative solution, Kubernetes allows clients to discover pod IP addresses through DNS lookups. And usually the way it works is that when a client performs a DNS lookup for a service, the DNS server returns a single IP address which belongs to the service. And this will be the service's cluster IP address, which we saw previously. However, if you tell Kubernetes that you don't need a cluster IP address of the service, by setting the cluster IP field to none when creating a service, then the DNS server will return the pod IP addresses instead of the service's IP address. And now the client can do a simple DNS lookup to get the IP address of the pods that are members of that service. And then client can use that IP address to connect to the specific pod it wants to talk to or all of the pods. So the way we define a headless service in a service configuration file is basically setting the cluster IP to none. So when we create this service from this configuration file, Kubernetes will not assign the service a cluster IP address. And we can see that in the output when I list my services. So I have a ClusterIP service that I created for the microservice and a headless service. Now note here that when we deploy stateful applications in the cluster, like MongoDB for example, we have the normal service, the ClusterIP service, that basically handles the communication to MongoDB and maybe other container inside the pod. And in addition to that service, we have a headless service. So we always have these two services alongside each other. So this can do the usual load balancing stuff for this kind of use case, and for use cases where client needs to communicate with one of those pods directly, like a master node directly to perform the write commands, or the pods to talk to each other for data synchronization, the headless service will be used for that. When we define a service configuration, we can specify a type of the service, and the type attribute can have three different values. It could be cluster IP, which is a default. That's why we don't have to specify that. We have a NodePort and load balancer. So type NodePort basically creates a service that is accessible on a static port on each worker node in the cluster. Now to compare that to our previous example, the ClusterIP service is only accessible within the cluster itself. So no external traffic can directly address the ClusterIP service. The NodePort service, however, makes the external traffic accessible on static or fixed port on each worker node. So in this case, instead of ingress, the browser request will come directly to the worker node at the port that the service specification defines. And the port that NodePort service type exposes is defined in the NodePort attribute. And here note that the NodePort value has a predefined range between 30,000 and 32,767. So you can have one of the values from that range as a NodePort value. Anything outside that range won't be accepted. So this means that the NodePort service is accessible for the external traffic, like browser requests, for example, at IP address of the worker node and the node port defined here. However, just like in ClusterIP, we have a port of the service. So when we create the NodePort service, a ClusterIP service to which the NodePort service will route is automatically created. And here, as you see, if I list the services, the NodePort will have a ClusterIP address, and for each IP address, it will also have the ports open where the service is accessible at. And also note that the service spans all the worker nodes. So if you have 3 pod replicas on 3 different nodes, basically the service will be able to handle that request coming on any of the worker nodes and then forward it to one of those pod replicas. Now, that type of service exposure is not very efficient and also not secure because you're basically opening the ports to directly talk to the services on each worker node, so the external clients basically have access to the worker nodes directly. So if we gave all the services this NodePort service type, then we would have a bunch of ports open on the worker nodes clients from outside can directly talk to. So it's not very efficient and secure way to handle that. And as a better alternative, there is a load balancer service type. And the way it works with load balancer service type is that the service becomes accessible externally through a cloud provider's load balancer functionality. So each cloud provider has its own native load balancer implementation, and that is created and used whenever we create a load balancer service type. Google Cloud Platform, AWS, Azure, Linode, OpenStack, and so on, all of them offer this functionality. So whenever we create a load balancer service, NodePort and ClusterIP services are created automatically by Kubernetes, to which the external load balancer of the cloud platform will route the traffic to. And this is an example of how we define load balancer service configuration. So instead of NodePort type, we have a load balancer, and the same way we have the port of the service, which belongs to the ClusterIP, and we have the NodePort, which is the port that opens on the worker node, but it's not directly accessible externally, but only through the load balancer itself. So the entry point becomes the load balancer first, and it can then direct the traffic to NodePort on the worker node and the ClusterIP, the internal service. So that's how the flow would work with the load balancer service. So in other words, the load balancer service type is an extension of the NodePort type, which itself is an extension of the ClusterIP type. And again, if I create a load balancer service type and list all the services, you can see the differences in the display as well, where for each service type, you see the IP addresses, you see the type, and you see the ports that the service has opened. And I should mention here that in a real Kubernetes setup example, you would probably not use NodePort for external connection. You would maybe use it to test some service very quickly, but not for production use cases. So for example, if you have an application that is accessible through browser, you will either configure ingress for each such request. So you would have internal services, the ClusterIP services that ingress will route to, or you would have a load balancer that uses the cloud platform's native load balancer implementation. So that was an overview of Kubernetes service types, the differences between them, and when to use which. I hope you guys got a lot of information out of this video. Let me know in the comments if you have any questions. What is your feedback for the video, or what other topics you want me to cover next? Thank you for watching, and see you in the next video.